So we're going to talk about homogeneous equations with constant coefficients. So what do we mean by these words? So homogeneous means that the differential equation is set equal to 0. And so we end up with things that look like this, maybe P of t y double prime plus Q of t y prime plus R of t y equals 0. So this is a second order differential equation because the highest, derivative that you see is a second derivative. It's a linear differential equation because it kind of looks like a polynomial sort of with derivatives of y and then these kind of coefficient functions of t in front. And this is homogeneous because it's set equal to 0. And so basically here we're going to focus on second order linear homogeneous differential equations where these coefficient functions the coefficient functions P of t, Q of t, R of t are constants. Okay, so they'll kind of look like this: ay double prime plus by prime plus cy equals 0. For constants a, b, c, elements of the real numbers. So here's an example. Solve the equation y double prime, y double prime minus y equals 0. And also find the solution that satisfies the initial condition y of 0 equal 2 and y prime of 0 equal 1, negative 1. Okay, so how do we solve this equation? So let's write down solution. So we're just going to kind of talk through the solution, and I really am going to I'm going to notice a few things here, but then I'm going to have a theorem that's going to give us kind of a strong result at the end of this. So this is kind of fiddling around until we get the theorem. So let's think about this differential equation. What is this saying? Y double prime minus y equals 0. In other words, we're looking for a function, a y function that is equal to its second derivative. Okay, so something that's equal to its second derivative. So, so you might think of the function e to the t. If I keep taking the derivative of e to the t, I just keep getting e to the t. So if I take the derivative twice of e to the t, I get e to the t again. So, and any constant times e to the t is going to be work. And also, if I have c e to the negative t, that's going to work. Now, the first derivative is going to be negative c e to the t, and then the second derivative is going to be negative negative, so you'll get a positive c e to the negative t. So these are both examples. So those are both examples of functions that are equal to their second derivative. So, so I'll put in parentheses, really they're the only ones. You don't know why that's true yet, but we'll have a theorem about that later. Also, any linear combination of these two is also going to be the function y equals c1 e to the t plus c2 e to the negative t also has this property, because if I take its first derivative, I'll get c1 e to the t minus c2 e to the negative t, and if I take the derivative again, I'll get the same thing. So let me go ahead and take its second derivative. And if I take y double prime, I get c1 e to the t plus c2 e to the negative t. So you can see that that function, c1 e to the t plus c2 e to the negative t, is equal to its second derivative. So that is a solution to this differential equation. So the theorem is going to tell us that this solution, that the solution must be of this form. Okay. So, all right, so we have a general solution. And that is y equals c1 e to the t plus c2 e to the minus t. And note that we have these two constants here, c1 and c2. I have initial conditions, and I can use those initial conditions to solve for c1 and c2. So to find a particular solution, we will use the given initial conditions to solve for C1 and C2. So we had this differential equation, y is this was our general solution. And our initial conditions were y of 0 is 2, and y prime of 0 is negative 1. And so this is our general solution. So I claim that we'll get, using this first initial condition here, I'm going to get 2 is equal to C1e to the 0 plus C2e to the negative 0. So 2 is equal to C1 plus C2. Using this initial condition, I'm going to get negative 1 is equal to, wait, what was y prime? C1e to the t minus C2e to the negative t. Okay, so I'm going to use this second initial condition is going to go with this one. My first initial condition went with that one. Okay, so my second initial condition is going to give me 1 is equal to C1e to the 0 minus C2e to the minus 0. So in other words, I get negative 1 is equal to C1 minus C2. So now I have this system of equations here, which I can solve, and I end up getting C1 equals 1/2 and C2 equals 3/2. So then my particular solution is going to be y equals 1/2 e to the t plus 3/2 e to the minus t. So the example suggests that solutions to homogeneous linear differential equations with constant coefficients are of the form e to the RT.
Excuse me.
So if we have the differential equation ay double prime plus by prime plus cy equals 0, and we're going to assume that y is of the form e to the RT, well, then that means y prime is going to be re to the RT, and y double prime is going to be r squared e to the RT. Then I plug those values in to the differential equation, and I get a r squared e to the RT plus b r e to the RT plus c e to the RT equals 0. Now notice that all of those terms have this e to the RT in them. So what I can do is I can factor that out. So then I'll get a r squared plus br plus c e to the RT equals 0. Well, what do I know about this exponential function here? I know that this exponential function, e to the RT, that there is no value of t for which that's 0. So the only way I'm going to get solutions to this is if this equation is equal to 0. Okay, and this equation has a special name. So the name for that equation is a characteristic equation. So this is called the characteristic polynomial of this differential equation. Okay, and so this differential equation is going to have is going to, the roots of this differential equation are going to give us information about the solutions to the differential equations. So we can see that the roots of the characteristic polynomial, AR squared plus BR plus C, will yield Okay, so what are the possibilities? So we'll have three cases. We have we have two distinct real roots is one case. Case 2, we have repeated roots. And then case 3, we will have complex roots. And so I will deal with each of these three cases in its own video.